Okay, everyone, so this is our last class before the final. And I just thought what we would do for our review today is just first start with a few eye-clicker questions that we didn't get a chance to do last time on the Spearman rank correlation coefficient. And I know some people had some questions on that anyway. So why don't you get out your eye-clickers and we can start with that. And then it's the same question. Okay, so here's the question. I'll show you. Let's do that first. All right, you might recognize this question as one of the ones on the practice parametric problems. They're on page 216 in your book. And I thought we might as well just start with this. So let's start this. All right, so let's see what you chose here. All right, so there's some uncertainty. Most people chose, what is this? This is A, B, C, D, and E. Did you get that mixed up? Maybe because you didn't see the letters there. You thought this one was. Anyway, the answer is none of the above. This one, which is E. So let's think about that. Here, let's get this out of the way. And look at this. So why is it none of the above? Well, how about you think about it this way? It says, okay, let's just do it in our own class. Let's say that I told you that your final exam scores had the same average and standard deviations as what our exam 2 scores were. Okay? Would you know what your final exam score was? You'd have no idea, right? That's what this is saying. It's saying the averages and standard deviations for both exams turned out to be the same. How does that tell you anything? Right? I mean, think about it. Math SAT scores and English ACT scores both have the same average and standard deviation. They're normalized to have it. But just because you get one score on one doesn't mean you know what the score on the other one is, right? All right, so it doesn't tell you anything. So it's none of the above because you don't know how the 2 sets of scores are paired up. Does that make sense? Okay, let's try the next one. Let's try the next one. And the next one is, all right, I'll start this. Again, sorry, this is A, B, C, D, and E. I gave you a big hint with the ACT scores or the SAT scores. Remember, they're normally distributed. All right, I'm going to stop it and see what you said this time. Bring it up. Okay, so most people got E. And and that's the answer, none of the above. All right, let's look at that. None of the above, again, think about it. Once you change sets of scores, you take two sets, let's say you have two normally distributed scores like SATs or ACTs, just because and they have the same average and the same standard deviation, like for once you change them to z-scores, they always do have an average of 0 and a standard deviation of 1. That doesn't mean you know how the two sets of scores are paired up. It doesn't tell you anything about the correlation, does it? No. It just tells you sort of the the spread of the scatter plot and the center, but it doesn't tell you what it looks like. It doesn't show you anything about how the points are matched up with each other. So, all right. Now, finally, let's look at the next one. I'll start this one. Okay, so we can stop it here and see what you said this time. All of the above. Okay, let's look at this. The answer is just that the rank Spearman is 1. It doesn't, you don't really know. Now look, we didn't say normal. Repeat part A. We don't know that they're normally distributed. Let's look at this. And so your answer is just that the rank Spearman is equal to 1. If I had added the extra assumption that they're normal, maybe you didn't see that. Repeat part A, adding, so you just know that they have the same averages and the same standard deviations, right? So I can see why you might have thought this. If I had added the extra piece of information that they were normally distributed, but you really don't know the distribution. You just know the ranks. Okay? Does that make sense? Yeah.
Can you clarify the question? I didn't quite get it. Like, when it says like the same student holds the top score on both exams, and it says that same student was the second top score for both exams.
Okay, he said clarify the question. It means that the person who got the highest score on the first exam also got the highest score on the second. So if you change them to ranks, you'd have the same exact ranks on both exams. So you know that this is equal to 1, because if you know you're the top score on one exam, you know you're the top score on the next exam. But does that mean the correlation coefficient is equal to 1? No, even though the averages are this, you don't know, you can't predict your exact score, right? I can't tell you, the top scorer might have scored a huge amount, like had a big distance from the next score on the first exam. So you don't know how their z-scores match up. Does that make sense? Okay. All right, so this was actually, let's go back to the document camera. And these are the same questions, I don't know, that are on page 216. And in these practice problems here. So, and these are also the same questions that are on the non-parametric practice problems for your final exam review. So the answer to this one was just, these are the same ones. While we're here, we might as well do question 3 as well. Look at the 3 data sets below. For which data set is the correlation coefficient equal to 1? And for which data sets is the Spearman rank order correlation equal to 1? So we can think about this. Okay, for the Spearman, here's our data sets right here. And now, if we wanted to change them to ranks, what would we do? Well, this one would be the same in ranks, wouldn't it? Wouldn't it be exactly the same in ranks? So this certainly has a correlation coefficient equal to 1. So we know that data set 3 is both, right? How about the other data sets? Let's look at the other ones. How would we look at this? All right, so now we want to change this one to ranks, and we change the x and y separately. So here you change 100, 200, 300, and 400 to ranks. That's 1, 2, 3, and 4. All right, and now we'll change the last 4 numbers to ranks, and what do we get? 1, 2, this is the smallest. They're in ascending order, so this is also 1, 2, 3, and 4. So there's these form a straight line, x equals y, that's the line here. So obviously this is for the Spearman rank data set, 1 has a correlation coefficient of 1, right? But does this have a correlation coefficient of 1? Does that form a straight line? No. So far only data set 3. How about this one? How about data set 2? Well, this one is what? 6, 5. So this is ranks 3, 2, and 1. And what are these? These are also 3, 2, and 1, right? So all of them, all have a Spearman correlation coefficients of 1. But do these form a straight line? No. So only 3. Only data set 3. All right, so that's some practice problems on the Spearman correlation coefficient. And all these practice problems here are the same as the ones on Lon Kappa. So you can do, these were going to be your homework, but instead I just have them as practice problems on Lon Kappa, so you can do them and check your answers. I don't think I need to go through them all here, because they're very similar to the problems that are in the practice exam, except for those few. All right, so how about if we just start with the practice exam? Is that a good idea for everyone? And let me just say a few words about how your exam will look before we begin this practice exam here. All right, let's see. Okay, so as I mentioned before, the final exam that you're going to be given is a Scantron exam, because we don't have time to grade it, because all the graders have their own finals and things are very rushed this semester. So I am translating, I'm changing all the problems, picking problems from the exams and from similar problems to what's on our practice final, and changing them all to multiple choice. A lot of them are already in multiple choice. But as a warning, I know everybody loves to fill in those tables and they really help you, but we can't really make those into multiple choice. We can't make any of the calculated. We'd have to just, for example, what we'll have to do is I could, just pick out certain cells and ask you to calculate them. So there's advantages and disadvantages. The advantage, obviously, for a multiple choice test is you don't have to do the calculations. You can guess, and you can work backwards. You can see the choices for the calculated and plug them back in and realize some of them couldn't be true. So it's going to be somewhat different because of that. Maybe some people like it better, maybe some people like it worse. And of course, there's no partial credit, which always helps people, no continued error. So what helps people tremendously on the exams I give is that I break them up into parts, and it sort of guides you along. And then the parts, I give you continued error. That's a lot of why people do so well in these exams. I treat them as a learning experience. I really believe exams should be a learning experience. So this final can't be quite like that. I don't feel as bad because the final is more of an evaluation than a learning experience. I mean, studying for it is a learning experience, but actually taking it is more of an evaluation. Whereas the exams, I don't believe are that way. I want you to learn while you're taking the exams, thinking about them and going over it and getting it back and learning from it, reviewing it. The final doesn't really have to be that way, so I don't feel as bad about making it multiple choice. But it is going to be probably just in multiple choice form. That means you're not guided along the way as much. Okay? And you don't get continued error. So there's advantages and disadvantages. It's the way it's going to be. I have no choice. Okay, so let's go through this. In the beginning, most of these, a lot of them are already in multiple choice, so they won't be a surprise. Okay, so power. Let's start at the beginning because I think a lot of you forget the beginning, exam 1, and I strongly recommend you go over your exam 1 and make sure you understand it. All right, so let's look here. Significance tests are always subject to two types of unavoidable errors, type 1 and type 2. All right, and so how should you, I gave this little chart, and how can you remember this? What is what? Well, if you think back to here, you can look down here, down at these little graphs here, and if you think of them this way, this is when the null, you're drawing a probability distribution when the null is true here, and when the alternative is true. And then you have these decision makers, this cutoff. And so it's subject to two types of errors. So, for example, here, when the null is true, when you reject the null on this side, right here, that's alpha, a type 1 error. When the alternative is true, that same decision maker divides the alternative curve. When the alternative is true, the alternative is you want to go for the alternative on this side. So beta here, this is your type 2 error. Same with all of these. Okay. All right. So basically, if you think of it that way, and then what is this? When you reject the null, you run the, if the alternative is true, sure, this is the probability that you're making a type 1 error. But if the, when the null is true, right? We set that. Here it's set for each one of these at 5%. So we set that. And then, depending on what your alternative is here, if you're on this side, well, that's called the power of the test, the power to detect an effect that's really there. And this is your type 2 error. You're making a mistake. If the alternative is true, you want to decide on this side, right? So this would be your power on this side. This one has a much bigger power, etc. So how to fill out this chart? When the null is true, right, then rejecting it is making an error. It's true. So this right here is type 1 error. And the type 2 error can only happen when the alternative is true. And you decide that you fail to reject. You say you don't reject it. When the alternative, if you're on this side, that's a big type. Here you have a big type 2 error. So you fail to reject it. So that's the type 2 error. And then the power can only happen when the alternative is true. It's the power to detect an effect that's really there. So this is your power right there. Okay, so this is C, and that's A. So just draw a picture if you can't remember it. All right, now is it possible to calculate the type 2 error from the type 1? Well, look, no. Here we have the same type 1 error in all of these, but the type 2 is very different. That depends on the particular alternative that we specify. Right? You need to know that. You also need to know the standard error, the standard deviation of the sample size. So you don't, when the null is true, where is that? If it's possible, no. Right? Okay. Now, a large randomized experiment is done to test the effect of what is possible to determine. The two that are possible are if you know the type 2 error, you could know the power. These two have to sum to 100. Okay, a large randomized experiment is done to test the effectiveness of some drug, and the researchers do a significance test and set alpha at 5%. So they're setting that at 5% like they did in each one of these. All right. How do I know they did? Because z is equal to 1.65. For a one-sided test, that would be 5%. Because z equals 1.65 has 90% in the middle. So that's, yeah. All right. So the difference in cure rates between the drug and the placebo is equal to 0, and the alternative is one-sided here. All right, when the null is true, what's the chance the researchers will make the wrong decision, the type 1 error, and decide the drug really doesn't work when decide the drug works, the false alarm, when it really doesn't, right? The null is it doesn't work. And so what's the chance? That's 5%. That's what this is right here. You're critical when you choose a null cutoff. You're choosing the probability of a type 1 error. That's what you're doing, which is 5%. Does that make sense? All right. When the null is false and the drug really does work, what's the chance where researchers will correctly reject the null? Well, do we have enough information? No. That's what we just talked about. That you need to know. You need to know what? The specific alternative. Specific hypothesized alternative value. And the standard error, too, to calculate that. And will I ask you what that would be asking you for the power of the test, right? That's what this is asking you for, the power. And we've done those calculations, and you should know how to do them. Now, are they going to be worth a lot if you have it on the exam? No. I would probably just give you the information, and then you'd calculate. Instead of going through all the steps, you just get the final result. And you could calculate either the power or the sample size if I gave you the power. I don't know if people want me to go over that now or go through the test, and at the end, if you want me to go over that, I can. Do you want to just go through this, and then if you want to see that worked out, we could do an example? Does that sound good? Might as well just get through the test and see how many people would want to see something like that. Okay, we'll go through the test then. Now, suppose the researchers specify an alternative that sets the cure rate for the drug at exactly the null cutoff. Wherever the null cutoff is. Which pair of histograms most closely depicts that situation where you're setting the middle of your alternative curve right at the null cutoff? Because the middle is where your the alternative hypothesis, like right here, that null cutoff is going right at the middle. Here it's not, and here it's not. But if you set it right at the middle here, you only have 50% power, right? And this is A, and you have 50% power. We never want to set it this side. Then that would be crazy. We figure, okay, we're going to reject the null beyond this point. So we want most of the alternative curve to be on the other side, not just half of it. So for example, in this one, what is the power of the test? When you set the alternative, when this distance right here, this distance, this z beta right here, is equal to here, the z beta is equal to 0. Here, the z beta is equal to what? That looks like what? Negative 1.65? So the absolute value of it is 1.65. So that would give you what? A power of what? 5% in this tail. Z beta would be 5%, and this would be 95%. And here, what is z beta? Z beta is equal to what? See, I'm talking about the distance from here to here. That's the absolute value of it is 1. That looks like negative 1 to me. So this would be what? 16% here, so this would be 84% there. And this is right at 0. So that's the idea. Okay. Now, let's look at these. I'm sure these are ones that people had a lot of difficulty with. They're ones, experimental design questions. Okay, so the exam 1 was very conceptual, and people just have trouble with power. Everybody does, and with confounders. So it was a harder exam for people. Of course, it's not going to be worth that much of the final, because remember, there's 4 parts to the final. There's exam 1 material, exam 2, exam 3, and then the post-exam 3 material that you've never been tested on. So these, if you mess up one little piece, it's not going to hurt your final grade that much. All right, so now your final exam score that much. A recent study found that students who took a test immediately after reading several passages about a scientific subject retained about 50% more information 1 week later than those who repeatedly studied the material without taking a test. This is a very good study advice. That's what I'm putting on the practice day. Take tests as real tests. Don't just like read over notes. Make sure you know how to cover things up and try to do problems all the way through. Okay, the subjects were 200 college students. Half were randomly assigned to read the passages and immediately take a test measuring how much they recalled, and half were randomly assigned to repeatedly study the passages by outlining the main points and writing down the key ideas. This has been repeated many times, and they find that it's extremely, nothing replaces actually taking the test. If you're going to take a test, you need to take practice tests as if they're real tests. Okay, 1 week later, all the students took a test measuring the ability to recall facts and draw logical conclusions. Those grading the test didn't know which students were in which group. Those in the test group both recalled more facts and were better able to draw logical conclusions than those who repeatedly studied the material. All right, what do you want it to trust? This first thing you have to notice is it's a random experiment. So they were randomly assigned to 2 conditions. All right? So if it's a randomized controlled experiment, what do you immediately know? You know that all the confounders are eliminated. Everything, as long as basically the groups are, the 2 groups are going to be the same on all variables within random error. And that's what we're measuring with the significance test, is the random error. So this is a perfectly designed, randomized experiments are perfectly designed to do these significance tests and to conclude causation. Which conclusion is best supported by the evidence? The study provides strong evidence that among this group, we can't necessarily extrapolate, of college students, that test taking was the better method of learning the material. It was randomized, so you can conclude causation. Because it's a randomized, all right, so we can conclude that. You can't just say it's not likely to have confounders, because there aren't likely to be systematic differences between the 2 groups that are associated with the outcome. This study only shows that it's associated. It does not show it causes, because to learn better, since the students themselves were not given the option to choose which study method they preferred. They weren't given the option, that's true. So we're just showing which that would have introduced a confounder. Then we wouldn't have known whether better students choose to take one over the other. Okay? Suppose I'd like to determine whether weekly quizzes work better than weekly homework to help students learn Stat 200 material. I decide to offer a 15-minute quiz at the end of every class and give everyone the option of at the beginning of the semester to be either in the here I'm giving the option. This is not a randomized. At the end of the semester, I compared the overall exam averages and find the quiz group did significantly better. Okay? So now it's not randomized. It's not historical. It's non-randomized controls. It's an experiment I do, but I let them choose. So that's certainly not randomly assigning them. Based only on the information, now which statement is best? Now, the experiment provides strong evidence that the weekly quizzes worked better. No, because they're two different groups of students. They were not randomly assigned. They might have been better students who chose to take quizzes because they know they do well on math tests or something. This experiment only shows that weekly quizzes are associated with better exam scores, not that the quizzes actually cause them. That sounds good. Let's read the third one. This experiment shows that weekly quizzes are associated with, but definitely do not cause. Well, we can't say one way or the other. We can't say it wasn't a randomized experiment. We can't conclude it either causes or does not cause. We just don't know. It could, but we just don't know. We have to do more. We'd have to turn it into a randomized experiment. So it's that one. So now below are either confounders that mix up the results, causal links that explain how quizzes cause better test scores, or neither. Okay, so you can just, given all this information, which one is which? So we're wondering, okay, we see this association. Are the quizzes actually causing the higher exam scores? They might be. If so, how? This would be the causal link. Or there might be some other variable, a confounder, this is what we're trying to figure out, that's both leading to people choosing the quizzes. They take the quizzes are a marker for this type of students. They chose to do it, and also leads to higher exam scores. And there might not be any connection between these two. And then maybe one's neither. So I'll give you a minute, in case you haven't done it, to just like figure out whether it's this or this, like which one is which. Just a minute, so you can do this one on your own, because I think it would help you. All right, so let's look at this. Math test-taking ability. The students who chose to do the quiz instead of doing the homework are probably better at math tests. So a higher math test than those who choose to take the homework. So where doesn't that fit here? If they're better math test takers, then they'd certainly probably figure, hey, I'm just going to take the quizzes. I'm pretty confident. I can do this stuff really easily. And that it's a mark. So these quizzes are a marker for people who are good at math to begin with and good at test taking. And that's why they get the higher quiz. You don't know if it was the quizzes causing them to do better. And so that's the confounder. And that is eliminated in random assignment. How about this? Options, allowing, let's look at what this would be. How would quizzes cause higher exam scores? Retrieval from memory rather than from notes. Those who take quizzes are forced to retrieve information from their memories rather than from their notes, and that process helps cement learning. I mean, it's the same process you use when you take an exam. You have to retrieve stuff from memory. So that would be a causal link. It would be how. And that's what people theorize is doing it. But we can't tell from this experiment. And then options, allowing students to choose the study method that works best for them, whether it's homework or quizzes, improves the learning environment for everyone. That might be true that it does, but it has nothing to do with this experiment because the evidence, there's no evidence for this. In fact, the homework group did worse than the, we're trying to explain why the quiz group got higher scores. And that is neither here nor there. That doesn't explain it. Sure, it's a great learning environment, but we just don't, it doesn't support it has nothing to do with what we're talking about. So that's neither. No evidence for this. It's not in the information given, and the homework group did worse. So I don't even know why this would be true. Okay, so that's pretty much that. Any questions on that? Okay, that was pretty straightforward. So now we're on the next one. And so this goes along with, okay, so we have, this is just very simple. You're given these 5 summary statistics, the averages and the standard deviations for a homework and final, and a correlation coefficient, and asked to find the slope and the intercept here. So this is very simple, and you're not going to be given this formula, so you might as well just make sure you know it. So this is R times S dy over S dx. For the slope, that's what's going to go right in there. And this is y, because that's what we're trying to predict. And this is x. So we have 0.3, and so is it just, here's your SDs, and it's y over x. So this is 0.6. Okay? And then to get the intercept, you just plug in the point of averages here. So this is pretty standard. So what would we plug in for final? We'd plug in 60. And for homework, we'd plug in 80. And we'd say what makes that true. So we have 48 plus what equals 60. So this has to be 12. All right. And now, any questions on that? So that's certainly something you should know. Now, a confidence interval. Okay, so first of all, you need to know what a confidence interval is. So the 95% confidence interval is always going to be what? The sample statistic. In this case, we're talking about the slope. So we're going to put in the sample slope. That's our point estimate. We're trying to put error bars around it. And then we have plus or minus, and then we have something that corresponds with 95%. And then we have times the standard error for the slope, because it's a slope. All right, so is closest to. So we can approximate it with 2 here. That goes with the 95. All right, so what do we want to put in for the sample slope? Well, what is that? That's 0.6. You see, this is no good. This is a continued error. This would be hard to, I'd have to break this problem up. This is an example of how you can't just have this type of thing, because if you get this one wrong, then this one's going to be wrong too. So, okay, so, and there's no continued error on multiple choice, so. But I could ask it a different way. But anyway, how would you do this? Now, this standard error for the slope is given to you. Make sure you look here, and you see it right here. Here's your standard error for the slope. Okay, so you're going to use that. So it will be, so 0.6 plus or minus, and then you have 2, and then you're going to use that, which was what? The square root of 1 minus r squared, 0.3 squared, divided by the square root of n, and where's the sample size? 100, times that same s dy over s dx. And when you do all that out, you just do that out, add and subtract, and you'll get, I got 0.6 plus or minus 2 times 0.19, so it's this one. This is a good thing about these multiple choice questions, is that you come up with the wrong answer. You know you did something. I mean, the answer is not there, so you know you did something wrong. So you can catch your own careless errors pretty easily. But I often use the most common mistakes as the other answers. So, I mean, the other answers aren't just randomly chosen, they're common mistakes. So you might find your answer there. Okay, now to test the null hypothesis. All right, that the population slope is 0 against the alternative two-sided that it's not 0. We'd compute a z-test. Well, what is your z-test usually? It's usually your observed, it's going to be, here it's the observed slope minus the expected slope over the standard error for the slope. So we know that's 0 here, so our observed slope was, maybe I should just write it, get the formula here. Our observed slope, that's r times s dy over s dx. And then I can just copy our standard error for the slope. What is that from here? And that's the square root of 1 minus r squared from the front over the square root of n times s dy over s dx. So those cancel out, and we come up with our familiar r over the square root of 1 minus r squared times the square root of n, right? You should all know that anyway, but if you forgot it, there's another way to do it. We could think of what the chi-squared is and take the square root of it. Or we could go down here. First of all, which one is this? That's this one. Square root of 1 minus r squared, and, wait a minute, no, it's r times the square root of n. What is n? 100, so it's not that one. Which one is it? It's 0.3 times 10 over this, so it's this one, correct? Right? It's r times the square root of 100. And r is 0.3 times that. Do I have that right in the back of the book? Just make sure I do. Oh, it looks different. The key looks slightly different than this. The key is a slightly different version, but that's the right answer. Does everybody see that? Okay, now, if you square the z-stat, what do you get? Any questions on this? This is 0.3 times 10 over 1 minus 0.3 squared. Now, if you square z, what do you get? Z squared is what with a simple regression? What do you think? What statistic do you get? The chi-squared. And then what do you get if you square the t? You get the f. This will help, too, with multiple choice, because you'll probably recognize it. So this would be another way to do it. For this, you could have done, or a lot of people know the chi-squared is equal, if z is going to be equal to the square root of the chi-squared, which would be equal to the square root of what? A lot of people remember this better. That's r squared over 1 minus r squared times n. And that's the same as that, the positive version of it. This seems easier for people to remember because we've done it so much. You just take the square root of it, and it's that. Okay? Does that make sense? Now remember, you can only do this when you have one slope. Once you start having multiple slopes, you have to use the chi-squared. All right, questions so far? Okay, suppose the p-value for that. Why don't you try this one first? Just see if you can fill this one in. first of all, look and see what the alternative is here. Two-sided. We have a two-sided alternative. So that will help you with this. What should we put in there? Equals. Because the z, remember the chi-square is always positive, so it doesn't distinguish between one-sided and two-sided. Right? So we have this with the z. If we got this p-value, and it's in a two-sided alternative, that means that the area here and here adds up to 0.22. Okay? And that's the same as what a chi-square statistic will get you, because we square both sides, so this will go on the other side. It will just be like the tail, the right-hand tail of the chi-squared. Now, what about the t-test? What should you remember about the t-test? It's fat in the tails. Both of these, F and T, are fat in tails. So, and the p-value, fat, so T is fat in the tails, fatter. So if you look over here, and that's 2.2%, this little bit, right? T, this is the Z, then T is going to be fatter in the tails. So it's going to have, the T will have a bigger area. Sorry, but it'll have this extra area, I think. So the T is fat in tails, and P is area of the tail. So it's going to have a bigger. All right? The T always has a bigger p-value. It's harder to reject the null with the T. Same with the F compared to the chi-squared. Bigger, fatter in the tail. All right. Now let's move on. So the two scatter plots below show heart rate versus temperature for males and females, and we want to see if we can combine these two into a single one multiple regression equation. So what are we predicting? Heart rate, we're going to heart rate from temperature, and then we want to put it into a multiple regression and include another variable, gender. Okay, so we want to look at it like that. We can do that, but would it yield exactly the same predictions for all values as these two separate ones? Circle one of those, see what you think. Okay, so what do you think the answer is here? It's no, because the two plots have different slopes. You need an interaction term. Different intercepts doesn't matter because this will take care of the different intercepts. But we need an interaction term. We need something that's what? An interaction term would be some gender times temperature, so that you have a different slope for the two depending on gender. Like it would have to have this here with, whoops, which of the following, this is the one it has to have, this interaction term, not this doesn't make sense. So if we look down here, which of the following multiple regressions yield exactly the same? Well, this is the only, it's either this one can't because it doesn't have an interaction term. This one can't because it doesn't. This one has the wrong interaction term. It has to be an interaction between the two predictor variables. This is not the predictor. This is a y variable. So this is bad. So now we're down to these two. So you just have to see if those are the right coefficients. And remember how we can do this. we can say, if you had to get this yourself, how would you do it? You start with male is coded as 0. So this right here works when you have 0 here. Excuse me, this part, this and this. When you have 0 for gender, let's think about it. That gets eliminated and that gets eliminated. And you're left with exactly this equation. So that's good for when, for males. How about for females? What do you want to put in each one of these? Well, remember what we want to do. You look up your female equation, and it says we want in front of temperature, because this is going to be a 1 for females, so we're going to get temperature added to that temperature. So we say 1 plus 6 plus what is going to give us our needed 3.1. So in other words, what we want to do is 3.1 minus 1.6, and that is 1.5. And same here for gender. You're going to put a 1 in here for females, and we want to get this, negative 237. So we say, what do we put in here? So this is where this right here, how did we get that? Well, that is, we want negative 237, it's just the difference between that, minus, what do we have already? 88. So minus negative 88 or plus 88. That's how you get that. All right, you did a lot of these, and people did very well on that. So the answer is this one. Okay, and same with this. People did very well on this. Now again, this is not multiple choice, so I would have to condense this somehow. You're not going to be filling out all these. I can change this into a multiple choice pretty easily though. So let's look at this. So how do I do this? How would you do this? You'd fill this in no interaction. This is super easy. What's going to go in here? Well, there's no interaction. 5 plus 6 is 11, so 7 plus 6 has to be 13. Or 5 plus 2 is 7, so 11 plus 2 is 13. Now, how about this? Well, so what are we doing? A and B are 2 drugs. The 4 numbers in the table indicate the mean response to neither A nor B, A alone, B alone, and together. Fill in the blanks so this data matches the model. So when A and B are both 0, you get 5 here. Right? Now when B is 0, what do you have to add when A changes to 1 and B is still 0? 6. That's plus 6. So that will go there. How about in this direction? When A is 0 and you're just going from, so that would eliminate this. A is 0, and now 5 plus 2 is 7, so that has to be there. And now there's an AB term. If there wasn't, what would it be? Let's see what we have to get. Okay, so we have 5 plus 6 is 11 plus 2. This is 13. So we have to add what to get this? The 20 there is 7. So that will give you the equation. All right. So can we move on? I think people did very well on that. All right, let's see how much further we have. Okay, I think we can keep going here. All right, so here's statistics below summarizes the statewide violent crime rate, the percent of the population living below the poverty rate, and the murder rate per 100,000 people for what? For each of the 50 states and DC. And here's the correlation matrix. So what are we doing? We're trying to predict murder rate from these 2 variables. And here's the correlation matrix between the 3 variables. Fill in the blanks. Well, along the violent crime has a correlation of 1 with itself, 1 here. And here, murder, this is going to be symmetrical. The correlation between these 2, between crime and murder rate, will be the same as between murder rate and crime. So that looks like that. Now, what's the slope? This is just R. The slope between what? Predicting murder rate from violent crime. So we want murder crime, that R, times the standard deviation of y over the standard deviation of x, so it'll be murder over c. Okay, so R, which one is that? That's this one right here, 0.844, and times the ratio of their standard deviations of murder. Where's the standard deviations? Right here. So we want the ratio of these two. Murder and what? Crime. So murder is 5.991. Oh, they're all here. Over, see, it's so much easier when you have them. You can just look down here. Over the crime. So it's these two we're talking about. All right, so it's this one. And now here's the multiple regression equation. Okay, and compare the violent crime, compare the slope in the multiple for, okay, so we're comparing this to that slope, which is 0.21, and we see this one is lower. Why did it go down? Remember why it goes, these are the partial slopes, partial. So it goes down because which one? Because of they're correlated. Basically you have crime and it's correlated. There's an overlap with poverty, and they're both predicting, when you combine them to predict murder, we're only looking at, in the multiple regression, we're only looking at the part of the crime that predicts murder after we've controlled for the poverty, and vice versa. And they're all positively correlated, so that's why it went down. So it's this one. All right, if they were uncorrelated, they'd stay the same. And if they were negatively correlated, it would be hard to sort it all out. They could go up or down, depending on how the three of them are related. So this is the only time when they're all positively correlated that you can actually know for sure, or when they're uncorrelated with each other. Okay, now we're going to this is part of the same problem. We're going to test the null hypothesis that both those slopes, that there's nothing in that model, that both the slopes are equal to 0. And the computer did this chi-squared F test, and you see portions of it below. However, doing a significance test really is not appropriate here, because it's difficult to translate this situation into independent random draws from a wider population. We have all data on all 50 states plus Washington, D.C. So it doesn't make sense to estimate some wider population, some unknown state. It doesn't even make sense, really. We have them, and how could we know? It's just not a good problem for doing a significance test. Of course there's differences between the states, because there's difference, not because it's silly to model it as random variation. So we have data, we already know the population slopes aren't equal to 0. It does not make sense to do this. So, but people do stuff like this all the time. So will the results tell you, like if you do the calculations, will they alert you that it wasn't appropriate? Yes, you'll get impossible results. Will that really happen? Negative, Yes, you won't be able to calculate test stats because you won't have all the numbers. Yes, the degrees of freedom won't sound correct. No, there's no way to tell from the calculations themselves. That's why we always have to check assumptions, because you can't tell from the calculations themselves. And one of the assumptions is that this is a random, that this method, you can model it on random chance. You could check if you looked at error plots and saw clumpings and stuff maybe, but not from the calculations themselves. Let's see, the value for the chi-square test is missing. Calculate it from the numbers, from the other numbers given, so let's see if you can proceed and everything looks okay. It will. All right, so So it's missing here. How do you do this? Do you remember how you would do this? Well, this is the chi-squared equals to what? R squared over 1 minus R squared times n. So you can do that. Because you have R and you have n. All right? So you can do that, and I got 151.84. Now here's the ANOVA table. Now, so how I know that people love filling out these tables. They're a great way to learn. We do so much work with tables, and that's the biggest drawback of this exam. I can't really have you fill in tables, which helps people. But I might ask you something like a particular cell in this table. So let's say I asked you to fill in this sum of squares. Well, how would you do it? I think we should look, you'll have to understand. So how do you do that? You would do what? Well, remember, this is SST. This is the whole crux of this. This is R squared times SST. You're dividing up this total variation into two parts. One's the proportion due to the model, the regression, and the other, 1 minus R squared, is the proportion left in the errors. So that's the idea. So if you needed to fill in that, your sum of squares model is going to be just your R squared times your SST. Okay? So that would be the idea there. So you just say 0.7485 times that would be your answer. I'm not going to fill in this whole thing. Let's, and then of course this plus this has to add up to this. Now, how do we remember the degrees of freedom and all that? Okay. First of all, what's our model here? Our model is we're predicting murder rate. Just think about what it is. And we have some intercept, plus then we have some slope times our crime, plus some other slope times our poverty. So right away you see the parameters are 3. This is poverty and that's crime. So you know 3 parameters, 3 betas. You have 2 slopes plus an intercept. You're estimating 3 things. That's the number of parameters. Now, remember your degrees of freedom so now the degrees of freedom for the model here, for the model, is always what? P minus 1. That's where that 2 is coming from. The degrees of freedom for the error is always what? N minus P. So that's what you would put in here. And the degrees of freedom total is what? N minus 1. So this is going to be 50. That's the easiest one to remember. And so you know this one has to be 48. And that is N minus P. P is 3. And N is 51. All right, now F. Well, this is really hard to write down here, but let's just write it. Can you tell from the calculations? No, you can't tell. But let's just, how would you get F? Well, F is going to be what? If you fill this out, it's just this over this. It's your mean square model over your mean square error. So it would be, and you could do it that way, but you also have R squared. And you can see that it's going to be exactly the same thing. Your mean square model is what? R squared times SST over 1 minus R squared times SST. So the SSTs cancel out. And this one is going to be divided by the degrees of freedom right here. Will be divided by the degrees of freedom, P minus 1. And this one will be divided by the degree N minus P. And so you just get your R squared over 1 minus R squared times what? When you N minus P over P minus 1. Or you could just, so you could do it that way, which is exactly the same thing as calculating this and then taking mean square model over that. Okay, any questions on that? I think you know how to do this, right? All right, let's move on. And I think this, let's see, is similar. What do we need to do here? Okay, So how are you going to remember the degrees of freedom here? Here, you're estimating, you have groups. So you're estimating 4 averages. So the number of parameters is equal to the number of groups here. Right? You're estimating these 4 averages. So 4 groups, so 4 parameters. So you have p equals 4 here if you were trying to do these calculations. And then what else do you have? P equals 4 and n equals 894. All right. So now so you could do the whole thing. So chi-squared, again, that's just going to be, what is your chi-square statistic going to be? Well, you're given r, so it'd just be 0.3 squared over 1 minus 0.3 squared times n. If you had to do f, it would be 0.3 squared over 1 minus 0.3 squared times what? Not 894, but what? N minus p, it would be 890 over p minus 1. So that's the difference between the two of them. That's why f is centered at 1, and this one's centered at its degrees of freedom. This is a squared. I mean, you can see this, that's what it looks like. All right, so how many degrees of freedom for the chi-squared? 3. How many degrees of freedom for the f? The f would have 3 in the numerator and 890 in the denominator. So what do you conclude when you reject the null? What? That at least one of the group averages is significantly different than the other. All right, now, so now when you want to test individual slopes, you can do this t-test. And what do you use? The standard error of the difference. What is it? Well, you can use this, I'm saying. That's really another way of saying the standard error plus is equal to 38.1. That's the same. That's equal to the standard 38.1. So we have that. Now what do we want to do? We want to combine, which one is it? We're comparing what to what? Small, big cities to what? To these small towns. So we're looking at these sample sizes here. And so it's this one. And the t-statistic is just going to be the difference between the means of those two in the numerator. So it'll be 53 minus 14. So it'll be 13 in the numerator. You know, your observed difference between those. Now, how many degrees of freedom? Okay. How many degrees of freedom for these? Well, the standard error plus that we're using in this is based on all the errors. We're looking at all the errors. So we should use the degrees of freedom. So use the degrees of freedom for all the errors, which is n minus g. So that would be 890. All the errors, n minus g. All right. Does that make sense? You're benefiting from all the data. Now, the p-value is that. So the Bonferroni correction has to look at how many possible comparisons you have, which is g times g minus 1 over 2. So this case would be 4 times 3 over 2, which is 6. So you multiply by 6. I'm trying to think what else we need to do here. We're not going to finish this all right now. Let me see what I could do. I don't want to rush through this. I could post the rest in another video. Would that be good? I'll just post the rest in another video. So I'll post from starting here in another video so you have time, because it's just too much right now.